M-theory, first proposed by Edward Witten in 1995, aims to unify all consistent versions of superstring theory. Now, before Witten's announcement at a string theory conference at the University of Southern California, physicists had identified 5 distinct versions of superstring theory. They seemed different, but researchers discovered intricate connections between them through mathematical transformations known as S-duality and T-duality. Witten suggested that these dualities implied a more fundamental theory, which he called M-theory. Think of M as standing for magic, mystery, or membrane, depending on your preference. Although we don't have a complete formulation of M-theory yet, it's believed to describe 2- and 5-dimensional objects called branes. At low energies, it should be approximated by 11-dimensional supergravity. Modern efforts to formulate M-theory often rely on matrix theory or the ADS CFT correspondence. Physicists are working on connecting M-theory to experimental physics, often by compactifying its extra dimensions to create models that might explain our 4-dimensional world. So far, none of these models have been verified in high-energy physics experiments, but the search continues. Einstein's general relativity describes gravity within the realm of classical physics. On the other hand, quantum mechanics, a radically different formalism, governs the behavior of particles at the smallest scales, based on probabilities rather than certainties. The problem arises when we attempt to unify these two theories. General relativity and quantum mechanics each work spectacularly well in their respective domains, but they clash when applied together, especially in extreme conditions like those found in black holes or the early universe. This is where the quest for a quantum theory of gravity begins. Enter string theory, a theoretical framework that aims to bridge this gap. In string theory, the fundamental building blocks of the universe are not point-like particles, but one-dimensional objects known as strings. These strings can vibrate in different ways, and their vibrational states determine the mass, charge, and other properties of the particles they represent. One particularly intriguing aspect of string theory is that one of these vibrational states corresponds to the graviton, a hypothetical quantum particle that mediates the force of gravity. By incorporating the graviton, string theory provides a promising pathway to a quantum description of gravity. Each theory allows different types of strings and exhibits unique symmetries. For instance, type 1 theory includes both open strings, which have endpoints, and closed strings, which form loops. Types 2a and 2b, however, include only closed strings. Remarkably, all 5 versions of string theory are now understood to be special cases of a more fundamental theory called M-theory. In our everyday lives, we are accustomed to 3 familiar dimensions of space: height, width, and depth. Einstein's general theory of relativity introduced a revolutionary idea by treating time as a 4th dimension, unifying it with the 3 spatial dimensions into what we now call space-time. In this 4-dimensional space-time, gravity is no longer just a force, but a manifestation of the curvature of space-time itself. However, what if our universe is not limited to these 4 dimensions? What if there are other dimensions that we cannot perceive directly? In string theory, space-time is 10-dimensional, comprising 9 spatial dimensions and 1 time dimension. M-theory goes even further, positing an 11-dimensional space-time with 10 spatial dimensions and 1 temporal dimension. Now, you might wonder, if these extra dimensions exist, why don't we see them? The concept of compactification provides an answer. In compactification, extra dimensions are imagined to close up on themselves, forming tiny curled-up shapes that are incredibly small, much like a garden hose viewed from a distance. To us, the hose appears one-dimensional, but up close we see its true multi-dimensional nature. S-duality is a relationship that tells us a collection of strongly interacting particles in one theory can, in some cases, be viewed as a collection of weakly interacting particles in another. In simpler terms, strong interactions in one framework can appear as weak interactions in another, and vice versa. Next, there's T-duality, which involves strings propagating around circular extra dimensions. T-duality states that a string moving around a circle of radius r is equivalent to a string moving around a circle of radius 1 divided by r. This means that all observable quantities in one description match those in the dual description. In general, duality refers to a situation where 2 seemingly different physical systems turn out to be equivalent in a non-trivial way. If 2 theories are related by duality, it means one theory can be transformed to look just like the other. Supersymmetry, often abbreviated as SUSY, is a theoretical framework that proposes a special relationship between 2 classes of particles, bosons and fermions. Bosons are particles that mediate forces. Think of them as the messengers of interactions between particles. Fermions, on the other hand, are the building blocks of matter, the very stuff that makes up the universe. So, what does supersymmetry propose? In a nutshell, it suggests that each boson has a corresponding fermion partner and each fermion has a corresponding boson partner. This pairing introduces a symmetry that, if present in nature, could solve many puzzles in modern physics. But the magic of supersymmetry doesn't stop there. When supersymmetry is imposed as a local symmetry, something remarkable happens. We automatically obtain a quantum mechanical theory that includes gravity. This is known as supergravity, a theory that seamlessly merges the principles of supersymmetry with Einstein's theory of general relativity. In the realm of string theory and its related counterparts, such as supergravity theories, a brane is a fundamental physical object that extends the notion of a point particle into higher dimensions. Imagine a point particle as a zero-dimensional object. Now extend this idea to a one-dimensional string, and then to even higher dimensions. This is where branes come into play. In dimension p, we refer to these objects as p-branes. When a p-brane moves through spacetime, it traces out p plus one-dimensional volume known as its world volume. We now turn our attention to the Kaluza-Klein theory. Inspired by the success of general relativity, physicists sought to extend this geometric framework to other fundamental forces. In 1919, Theodore Kaluza made a bold leap by proposing a five-dimensional spacetime, ingeniously unifying gravity and electromagnetism into a single force. This idea was further refined by Oscar Klein, who suggested that the additional dimension could be compactified into a tiny circle with a radius on the order of 10⁻⁻30 centimeters. Yet the seeds sown by Kaluza and Klein would not remain dormant. One approach to formulating M-theory and studying its properties is provided by the anti-de Sitter conformal field theory, ADIS CFT Correspondence. Proposed by Juan Maldacena in late 1997, the ADIS CFT Correspondence is a theoretical result which implies that M-theory is in some cases equivalent to a quantum field theory. In the ADIS CFT Correspondence, the geometry of spacetime is described in terms of a certain vacuum solution of Einstein's equation called anti-de Sitter space. In very elementary terms, anti-de Sitter space is a mathematical model of spacetime in which the notion of distance between points, the metric, is different from the notion of distance in ordinary Euclidean geometry. It is closely related to hyperbolic space, which can be viewed as a disk as illustrated on the left. One can define the distance between points of this disk in such a way that all the triangles and squares are the same size and the circular outer boundary is infinitely far from any point in the interior. Three-dimensional anti-de Sitter space is like a stack of hyperbolic disks, each one representing the state of the universe at a given time. One can study theories of quantum gravity such as M-theory in the resulting spacetime. An important feature of anti-de Sitter space is its boundary, which looks like a cylinder in the case of three-dimensional anti-de Sitter space. One property of this boundary is that, within a small region on the surface around any given point, it looks just like Minkowski space, the model of spacetime used in non-gravitational physics. One can therefore consider an auxiliary theory in which spacetime is given by the boundary of anti-de Sitter space. Another realization of the ADS CFT correspondence states that M-theory is equivalent to a quantum field theory called the ABJM theory in 3 dimensions. In this version of the correspondence, 7 of the dimensions of M-theory are curled up, leaving 4 non-compact dimensions. Since the space-time of our universe is 4-dimensional, this version of the correspondence provides a somewhat more realistic description of gravity. Introduced by Aharoni, Bergman, Jafferis, and Maldacena, the ABJM theory is closely related to another quantum field theory called Chern-Simons theory. The latter theory was popularized by Witten in the late 1980s because of its applications to knot theory. The ABJM theory serves as a semi-realistic simplified model for solving problems that arise in condensed matter physics. In this version of the ADS CFT correspondence, the 7 extra dimensions are compactified into a 7-dimensional sphere. As we delve deeper into the realms of M-theory, we encounter the fascinating field of string phenomenology. String phenomenology builds upon the idea of compactification. In this process, physicists start with the 10 or 11-dimensional spacetime proposed by string or M-theory and postulate specific shapes for the extra dimensions. By carefully choosing these shapes, they can create models that closely resemble the standard model of particle physics, while also predicting additional yet undiscovered particles, often supersymmetric partners to known particles. One popular approach involves the heterotic string theory in 10 dimensions, where the 6 extra dimensions are assumed to be shaped like a 6-dimensional Calabi-Yau manifold. Named after mathematicians Eugenio Calabi and Xing-Tung Yau, these manifolds offer numerous ways to extract realistic physics from string theory. However, constructing these models is not without its challenges. Theoretical and mathematical complexities, combined with the extraordinarily high energies required for experimental verification, make it difficult to test these theories. As a result, there is currently no experimental evidence that definitively supports these models as the fundamental description of nature. Because of the difficulties with G2 manifolds, most attempts to construct realistic theories of physics based on M-theory have taken a more indirect approach to compactifying 11-dimensional spacetime. One approach, pioneered by Witten, Horova, Bert-of-Root, and others, is known as heterotic M-theory. In this approach, one imagines that one of the 11 dimensions of M-theory is shaped like a circle. If this circle is very small, then the spacetime becomes effectively 10-dimensional. One then assumes that 6 of the 10 dimensions form a Calabi-Yau manifold. If this Calabi-Yau manifold is also taken to be small, one is left with a theory in 4 dimensions. Heterotic M-theory has been used to construct models of brane cosmology, in which the observable universe is thought to exist on a brane in a higher dimensional ambient space. As we draw the curtains on our deep dive into the captivating world of M-theory is not just a collection of abstract mathematical concepts, it's a living, breathing field of study that continues to evolve with every new discovery.